Our next talk is also an invited talk, Superconductivity in Infinite Layered Nickelates, Ariando from National University of Singapore.
Right. So good morning, everyone. Well, actually, I can just jump directly to my conclusions now because everything has been said by Carstens. Anyway, so maybe it's still good for those who didn't follow this history of the nickelate, so I can still start with very basic things. So I'm going to talk, well, maybe I like to make a disclaimer first about my name because Carsten keeps saying Ariando. Just to be clear, I have a single name, Ariando, I mean formally. So this is quite common in our country, so nothing illegal about that. But because of difficulty traveling, so and also with a scientific community, so I create this name Ariando. Well, formally. So I'm going to talk today more from the experimental perspective and show some result and try to compare this with the cuprate. So let me start. I'm from National University of Singapore. Just to acknowledge the people who are doing this. So these are two of my students who really are doing this work. Well, of course, supported by many other people in the group. And our penetration depth is done by Albert Chia from Nanyang University of Technology. And we also did a high magnetic field experiments, and this is mostly done in Toulouse, and right now it's also in Los Alamos. And high resolution TM done mostly by Penny Cook initially, but now transferred to Peter in Max Planck. And millikelvin experiment done in Hong Kong by Professor Goh and his group. So I also like to acknowledge the funding agencies, National Research Foundation of Singapore, Ministry of Education, and Agency for Research and Technology, ASA. All right, so again, why we are doing this one, come back to this complex phase diagram of the cuprate. So we know that there are these many fluctuations surrounding the superconducting dome. So this can be possible, leading to possible different mechanisms that we still need to understand. So to help this one, the main motivations why we do the nickelate, I mean, this has been done, of course, in the last 30 years. So can we find a cuprate analog to this to better understand the high Tc? Right? Oh. Right. So as a guiding principle, and naively, right, we can think about this square lattice of the cuprate as a starting point. And then we have this two-dimensional nature with a single orbital Hall filling. And then, of course, the antiferromagnetic ground state. So looking into this all, so nickelate has been proposed to be a promising system because, well, in principle, to get the Hall filling, you can go from you can do different orbitals, 3d7, 3d5, 3d1, but nickelate promise to have this 3d9 if you can make it nickel 1 plus. And this is not a stable system, so naturally you will get 2 plus or 3 plus. So to be able to produce the nickel 1 plus, you have to do something, which is trying to remove the apical oxygens in the perovskite structures. Okay? So this has been proposed to be a system that can, have this all different ingredients that I mentioned before. Right? So with this, you can achieve this 3d9 orbitals. And the question is, of course, whether you can isolate these Hall filling orbitals of the 3d9 in the nickel 1 plus. So by removing the apical oxygens, and then you will get this planar structures, right? And these planar structures, crystal field, will lead to the isolations of these z orbitals of the 3D. So leaving the xy minus y square high in energy isolated. So basically now you can fulfill all the ingredients that this copper oxide have. Okay. All right, so with that in mind, in the last 30 years or so, people have been trying to do this, trying to achieve this nickel 1 plus, including, for example, doing super lattices, trying to induce a charge transfer to be able to come to this nickel 1 plus state. And only recently, Dan Feng Li in Stanford, Wang's group, that produced this superconductivity in the ND doped by strontium. So as you can see here, the TC is around, so by starting with the dope NiO, and then reduce the apical oxygens, then you go from this perovskite structures to the infinite layer structures, and then it give the, so the parent compound itself, after the reductions without strontium doping, has these metal insulator transitions, weak localizations at low temperature, while the dope one has this TC around between 10 to 15 degrees. All right? And well, within half years or so, we have been able to reproduce this system. Then we developed this doping dependence of these ND-based nickel superconductors. And as you can see here, so the left one is the resistivity of the perovskite structures with this metal insulator transition in the parent compound. And then as you dope, then it's become a metallic system. So as I said before, so for doping around 0.1 also to 0.25, so we have been able to produce transitions, from very low few Kelvin to 15 Kelvin transitions temperature. Right, so more or less this is what we have obtained these days. So this is different nickelate superconductors, ND-based, lanthanum-based with strontium or calcium dopings, right? And also recently, based on this N5 of the multi-layer analogues of the infinite layer from the Rudelston-Popper compound. So Mundis and his group, has been able to produce this superconductivity as well, as even though the TC is very, very low, it doesn't reach zero resistivity. And of course, there have been also a couple of other groups that have been able also to produce superconductivity in this nickel-based superconductor. Right, so is this new nickelate really like cuprate? So here, if we look to the 3D electron counts, when we plot the TC as a function of 3D electron counts, as you can see here, so it kind of replicate what we have in the cuprate, right? So even though within a smaller doping range, but within the same amount range of 3D electron counts that you produce the superconductivity. So this is also where this the Rudelston-Popper compound picture comes into from this 3D electron count. As you can see, if you start with a 3-layer system, then you are still away from the dome, then you need to probably play with the dopants. While in the case of the Julias, so she did the 5 layers, and then you come directly simply based on the self-doping within the regimes of this superconducting nickelate dome. And then, well, there's, of course, this is kind of the similarity, but of course you also notice there are differences. For example, in the case of the cuprate, we have this antiferromagnetic and parent compound, while in the overdoped regime, for example, you have a metallic state. While as you can see here from the first diagram of the nickelate, in the case of ND, so both underdoped parent compound as well as the overdope, they shows this weakly insulating behavior. So it's basically a metallic with a weak localizations at low temperature. Also, as you can see here, so this is the temperature where you have a crossover between electron and hole dominant carriers. So if you go from underdope to overdope, you have transitions between electron dominant carriers to hole dominant carriers at different temperature depending on the amount of dopants that you have. Right? So as you go down, for example, for 0.2, which is kind of considered as optimally doped. So you start with the electron dominant carriers, but then around 80 or so, then you start to have whole dominant carriers in this 0.2 ND based system. So this change of the dominant carriers is not just as functions of dopant and temperature. We also notice as we play with the thickness of the system. So when we go from the very high thickness, high means around 10 to 15 nanometers, go down to around 4 nanometers, then you also see a crossover of the dominant carriers. So if we look to the resistivity behavior, so this is in the case of the optimally doped. So it shows this strange metal behavior linear with T dependent, like what we have also in the cuprate. But if we look into the overdoped regime, so it's a bit more complicated. So within a particular regimes, I don't show it here. You can fit with a different dependence of temperature. But dominantly, as you can see here, at very low temperature, you have this upturn, which is different than what we have in the case of cuprate. All right, so I just try to relate a little bit with what people have predict to DFT, and Carsten has discussed this a lot. But as we can see here, so this is without correlations, of course, and we have heard correlations, and maybe Frank is going to talk about more today. So we can see at the Fermi level is very busy orbitals that we have, so occupied by combinations between nickel 3D and the 5D hybridized state. So it's dominantly the Fermi surface having this 3D x squared minus y squared. And then at the A point, so you can see this pocket of hybridized ND5 dxy and probably interstitial S state. So as well as at the center of the gamma point, you also have this ND 3z squared minus r squared orbitals. So if we try to relate to what we have observed from the transport, for example, so we have this Hall coefficient, so this might explain or somehow consistent with the having this multi-band structures from the DFT. So the idea of having self-doping, it might also lead to these differences that we observe between the cuprate and the nickelate. So, and that's also probably the reasons why we don't have this mode insulator parent compound. As I said before, we have this weakly insulating behavior. And then there are many other experiments that I'm not going to talk today, but just to highlight. So for example, from the EELS and XIS absorption spectroscopy, it's kind of consistent also having this less hybridizations between the oxygen 2p and the nickel 3D in comparison to strong hybridization that we have in the case of cuprate. So this also leads to the idea that in the case of nickelate, we are, from the framework of the Zanen, Sawetzky, Allen, that we have this Mott-Hubbard framework rather than the charge transfer as in the cuprate. And from the rigs, for example, we do notice some kind of magnetic excitations, but there is no long-range order, and the coupling energy is much lower than what we have in the cuprate. So this again maybe something that have to be clarified, whether this is something to do also with the, for example, lower TC that we have. And then report on charge order that has been proposed by different groups. But again, here there is an inconsistency that needs to be further clarified. So what really the challenge from the experimental point of view, all right? So as I demonstrated before, all of those data simply based on thin film samples with a thickness ranging from 5 to 12 nanometer. And even for these samples, right, you are dealing with many different issues with crystallinity. You have stacking faults, secondary phases, and so on, that you really need to take care of before you can make a conclusions based on the experiment that you do. So there is, of course, no bulk single crystal yet that shows superconductivity. And the rate of that you can reproduce the sample is relatively low. Okay, and again, as you can see, there are only a few groups that have been able to produce. So it looks like to us that reduction is really the main issue, the removal of the apical oxygen, because we really don't have control in this way, in doing this one. So of course, this also creates issues with many experiments that we are not able to do, at least conclusively at this point, like ARPES, NMR, and so on. So what we do in our lab is doing pulse laser depositions. People have done also using molecular beam epitaxy. And this is how our system looks like. And then this will be subsequently followed by apical oxygen removal by calcium hydride soft chemistry reduction. And as you can see here, in terms of the perovskite structure, is perfectly fine, as you have this reed oscillation show that you have really layer by layer in the perovskite structures. So the surface of the substrate before and after the growth, and even after the reductions, you can see this nice step of the STO substrate, which indicate, at least in terms of the perovskite structures, you should not have a problem in trying to reproduce the sample. So again, the problem looks like in the soft chemistry process. So ideally, what you will have during the reduction is the oxygens will start to be removed alternatingly, right? And then as you continue this process, and then you will produce the infinite layer structure, all right? So this is the thing that we really having a problem with. This is difficult to control. So ideally, it would be nice if we can really look into the oxygen state, the different reduction steps, even if we can do it real time, okay? And then Carsten has proposed the idea of the hydrogen issues in this nickelate as well during the reductions. So what SIs that we are able to do now is really based on three things. So we look into the so-called lower fringes in the XRD. And then using high resolution STM, we try to confirm. Of course, this is going to be a very slow process. As you are aware of, STEM is a very tedious thing to do. And then, of course, resistivity is another hint that we can really use to judge the quality of the sample, whether we are going to be able to produce superconductivity or not. So in the last few years or so, try and error is really the main thing that we are doing here. So hundreds of samples every month that you need to produce to be able to do experiments to produce superconductivity. And we have been playing also in doing different way of reductions process, trying to do a matrix, trying to combine between having a high reduction power as well as quality of the crystalline samples that you're going to produce. For example, this is probably a good hint for people who are also interested to do this. We have been trying to use similar approaches, Harvard one, and we have not been able to do the same. We have not been able to do the same process. The sample is not superconducting. So it looks like this is the problem. So you cannot really, so it's really have to be optimized with your own system, especially this reductions power of, of this apical oxygen removal. So anyway, I'm not going to discuss this in too detail, just to highlight the sophisticated process that need to be done to really optimize your samples. So at least up to this point, we are now at a state much better than the initial samples. Oh, sorry. Where did I? Okay, maybe I point out here again, as you can see here, in the initial batches of samples, you notice there is no lower fringes. And this somehow associate with the high off-tilt structures, secondary phase that you have, and you only have this infinite layer up to probably around 5 nanometer, kind of a nice structures. Beyond that one is still, the density of this secondary phase is really large, as you can also see here, right? And this is from Howard-Wang's group, so it's kind of consistent. Having no lower fringes is associated with a large density of secondary phases. Now, as the process has improved a lot, so let me call high crystalline samples, right, in a quote. So you can see the density is much lower with a very clear lower fringes, and of course, the resistivity is also consistent with having superconductivity at the end. And this is also somehow consistent with Howard-Wang's group. So this is what they call the high crystalline samples, and they also start to see these lower fringes. Okay, so these are the eyes that we are using right now to try to look into our samples. But just to point out to Carsten's point just now, claiming that this is a high quality sample is not really true, because in the previous sample it's also within 5 nanometer, you always have a very nice infinite layer. While this sample is actually limited only to 5 nanometer. So it's not a thick sample. So that cannot really be said that for high quality samples in the case that you put this on the LSAT substrate. All right, so at least having this so-called quality samples, now we have been able to produce and also try to do different experiments. So the next 2 slides, I'm going to discuss 2 main experiments that we have done recently. So as you can see, again, the lower fringes quite a good high resolution TEM data, very relatively sharp transitions, and you can observe DC diamagnetic response directly from this sample, high quality sample. So one of the questions, of course, the pairing symmetry, and experiment has been done before by STM in a group of China. As you can see here, at the different locations on the same sample, you see this V-shape or U-shape features of STM. So there are kind of mixed conclusion from here, either whether there is really an actual mixture of the symmetry or simply because of the inhomogeneity of the samples at the different locations. Okay, so because of the limited samples, what we are able to do so far is doing London penetration depth, is basically looking into the response of the samples as you apply magnetic field and the resonance frequency of the LC circuit, and this difference in the change of the resonance frequency will be proportional to the change in the penetration depth at very low temperature. So we have to aim at very low temperature, so millikelvin, 100 millikelvin. And this, of course, the London penetration depth will be proportional to the gap of the system. And you can look into the fitting and the power dependence of this one, then you can classify whether something related more to the D wave or S wave, or the mixtures of the D wave or S wave. So as you can see here, so I only show 2 data here, but we have done very intensive analysis on this one. So none of them that show pure symmetry with a nodal behavior, right? So there is always some kind of not less features that have to be included in the fitting. Okay, so we cannot really claim that it's a pure D wave, right? So in the case of lanthanum base, for example, there could be a mixture between between S wave and D wave, while in the case of ND base system, it's difficult to say. So in conclusions, what we can say, there could be this multi-gap that we have in the nickelate system rather than a pure D wave. So another interesting thing is the upper critical field. Howard Wang has reported before that there is this isotropic Pauli-limited behavior in the case of the ND nickelate, and as well as the upturn at very low temperature. Okay, but when we do this, especially in the system based on lanthanum, as you can see here, the Pauli-limited is violated. Okay, 3 times of the limit of the critical field based on the Pauli-limited simple BCS idea. Okay, while there is a slightly different features in the case of the ND, where we don't see this upturn as we really go down to a very low temperature, 10 millikelvin. So these violations of this Pauli-limited behavior is really a tricky thing that we cannot really find reasons right now. Because if we look to the BCS, you might have these violations, but it's not in a way that similar to what we have. For example, you can have ideally you will have this Pauli-limited one, both in the case of in-plane and out-of-plane applied magnetic field. So the out-of-plane magnetic field probably related to the orbital effect, while in the case of the in-plane can be because of the paramagnetic Pauli effect. Okay, while in the case of this lanthanum nickelate, the violation is in all directions. Okay, in all directions of the crystal axis. So you can have violation, for example, in one of the directions, which has been shown in the case of the tri-layer drive-in, right? And this can be nicely explained by having a spin-orbit coupling locking your Cooper pair in one of in the plane, for example. Okay, and there is also small violations that sometimes observed in the case of, for example, the multi-band iron-based superconductor, but never been seen that it is, like 3 times of the limit, the Pauli limit. Okay, so this is something that we really struggling to understand and trying to do more experiments right now to really pinpoint the reasons for these violations of the Pauli limit of the critical field. So if we compare to the heavy fermion, for example, this is the only thing that we can see that there is this violation in all directions, which is significant. And this is, of course, the triplet superconductor, P wave. So whether this is something to do with this one is probably very, difficult. You need to really do, for example, the other experiments to confirm the reasons for these violations. Well, just to conclude now, there are differences, of course, there are similarities in the case of cuprate, but it's not just limited to the cuprate. We also notice this, in the case of the violations of the critical field, you need to learn more from the heavy fermion system, as well as this Moire graphene that kind of having some similar features. So more things that can be done, for example, to try to also produce system that is dominantly electron doped, right? In the case of superconductivity, as well as, of course, producing bulk superconductors, and then probably a new system without the self-doping that probably create differences with the cuprate that we observe so far to make it more pure, closer to what we have in the case of the cuprate. All right. So with this, I thank you for your attention.
Thank you. Any questions?
So you associated this weak upturn of the resistivity to Anderson localization, which is, given that it's a weak effect, quite reasonable. Have you or other experimentalists been able to prove this more by correlating the strength of the upturn to the disorder, or by applying a magnetic field, so that if it's Anderson localization, it should then go down the resistivity?
No, yeah, this is something have to be done, I think. Yes, thank you. That would be a good thing to do.
Any other questions?
would just like to ask, is there any way to determine that the Fermi surface where the band crosses, okay, the Fermi energy, that it is oxygen dominated or nickel dominated? It is predominantly D wave orbitally or P wave?
Probably this, well, to my understanding is yeah, it's
No, but the
so there is
question.
still oxygen contributions, I believe. We observe this in the case of thickness dependent, where there is a change in the pre-peak before the main peak of the nickel, which is likely because of the hybridization between the 3D and oxygen. So I think dominantly is 3D xy minus y square with a small hybridization with oxygen.
Okay, thank you.
It's a really nice talk. I think 2018 we were also try to adopt the nickelate to see the superconductivity, but we didn't succeed. But it's nice to see your accomplish. My question about the phase diagram. You have a phase diagram on the dome shaped. You have two hills, and
Yeah.
because of the transition from the electron dope to the hole dope, what I expect, there should be some separation. If we are talking about if it's similar to cuprate, and at the low, I think compensation of the carrier compensation, and then what I expected drop down to the TC, and then to see some kind of the Pissudy gap or some kind of the correlation effect, and then again the hold up regime, then we can see another dome shape phase diagram. Can you just explain why you have this kind of to combine the phase transition?
I don't think there is a concrete proof that this is intrinsic things that deep in the superconducting dome. And personally, I believe it's more like sample to sample quality variation still in this case. We have reproduced the phase diagram with a better quality of sample. So this one that I showed is really the first one. And we don't have that deep anymore. So it's really just a single dome. So there might be, I don't know, but at least there is no concrete proof that it is really the intrinsic things in this case of nickelate.
Any other questions? If not, we thank the speaker again.
Thank you.